So we're going to resume with methods of heat transfer. At CSEC level, heat transfer is not a calculation topic, so it's just a reading topic. But y'all at CAPE, everything is maths. So let's see what we have. There's some of them is common sense, some of them is a little new knowledge. So let's see what we are going to work with continuing on. So heat transfer, reading from the screen. There are many ways in which heat can be transferred from one place to another. Here we shall briefly look at how these methods occur, their nature and limitations. There are three methods of heat transfer that we will look at in this section that is required by the syllabus. So we have conduction, convection, and radiation. So we have a nice little diagram here to show you all our heat transfers in one little diagram. We have radiation, where you can encounter heat due to electromagnetic waves. We have conduction, that is where heat travels along a solid material, solid or liquid material. And convection is the movement of currents through a fluid. And fluid, by physics, is considered or classified to either be a liquid or a gas. So we cover everything here. Our three main forms of heat conduction are conduction, convection, and radiation. Conduction. Conduction is the transfer of heat from one molecule to another. This is a result of the vibrational energy found within the atom itself. Conduction occurs best through solids since their molecules are close together. Some solids, however, do not conduct as well as others owing to their chemical or their actual bonding makeup. Metals conduct heat better as opposed to non-metals, example, wood, plastic, fabrics, and whatnot. A good conductor of heat will feel cool to the touch because it pulls heat away from your hand very quickly, hence making it cool. So an easy way to determine whether or not something is a good heat conductor. Conductor means it takes heat very easily, it transmits heat very easily. If you have a metal container, like here, oh, this have water, right? Touch a metal container, especially like right now, you're going to realize a metal container feels cool immediately as you touch it, right? And it starts to warm up pretty quickly. Go and touch something that's not metal, right? And you're going to realize it takes a little while for it to start changing temperature. Why? Because the metal pulls heat away from your hand. That's how your hand feels cold. Anytime you touch something and you feel cold, it actually is pulling heat away from your fingertips, and your hands are going to record or notice that your temperature is changing because you're pulling heat away from it. So what does it do for conduction, for heat conduction? It's really, really simple. What it does, we know that solids vibrate, right? The molecules are only allowed to vibrate, back and forth very rapidly. And if I add heat to one molecule, that molecule now is going to vibrate even more than before. And guess what? It's now going to pass on some of that energy to the nearby or to their neighboring molecules. So it's now going to give more energy to their neighbors. And those neighbors now are going to vibrate more and more. And by vibrating more and more, they now are also going to start heating up. All right, so their temperature is going to heat up. So that's why when we have solids, the initial point where we apply heat is always going to be the hottest. So here will be hot, and the next corner will be cold. A good example, you all can try this afterwards. Take a metal spoon. We all have done this. If you take a metal spoon and leave it in your hot cup of tea, right? Go and drink a cup of tea after the class or during the class. Put a metal spoon in your tea. You're going to realize the part of the spoon that's in the hot tea is going to be hot, and the edge of the spoon is going to still be cool. But leave it for a little few minutes or a couple of minutes. You're going to realize that the entire spoon now is probably too hot to handle. Why? Because the heat. So this is the side of the spoon now is in the hot tea or coffee or whatever you're drinking. The heat here will start moving from one molecule to the next, to the point where all the molecules now are hot. So that's what we call conduction. Conduction is where heat moves from one molecule to another by vibration. So it's just sharing the energy, passing the energy down the line. Now, conduction takes a while to happen. Some materials conduct heat far better than others, while some take forever. All right, we have simple example here. You all can do this at home, but I really don't suggest that you go and put a pot spoon on the fire. Don't go and do that because you're going to get a burn, but you can try it and see. Same thing if you're cooking food and you're turning, leave that pot spoon in the fire or you leave it in the pot. You know, I quarrel with my mom about this all the time. Why do you leave the spoon in the pot while the food is cooking? The spoon is going to get too hot to handle. But I'm sure you've noticed this. If you leave a pot spoon in your food, in the pot of cooking food, the spoon is going to get too hot. Why? Because if this is your pot of food here, the heat is going to move along your spoon to the edge where you're supposed to be holding it. And if it doesn't have a plastic um, covering at the end, you're going to burn your hand. So continuing, liquids are generally poor conductors of heat. Generally. We're not saying liquids cannot take heat. That makes no sense because when we boil water, water gets to 100 degrees Celsius, that'll burn up our skin. Right? But liquids take a long time to conduct heat. Compared to metals, they take far longer. All right, try the same thing. If you put the pot on the stove that's empty with water, that gets hot within a couple seconds. But a pot full of boiling water to boil, you can keep on putting your hand and putting things in that water for a little while before it gets too hot because water takes longer to heat up because it's a poor conductor of heat. They take very long to heat up and very long to cool down. Similarly, if you take a pot, put it on the stove, let it get hot, take it off the stove, take off the fire, walk away from that pot or go and do something within a few minutes, that pot is hot enough to handle. If you have a pot of boiling water, you take it off the fire, you can walk around, go wash your wares, and you still can't touch that water because it's too hot. Water takes a long time to heat up and it takes a long time to cool down. Gases are even poorer conductors of heat. As a result, air-filled pockets make extremely good heat insulators. An insulator is something that prevents heat from flowing. It's the opposite of a heat conductor. Just like how we had electrical conductors and insulators, same thing. So here we have a conductor and an insulator. The general word means conductor means we allow for the free flow of something. Insulators mean we prevent it from happening or we prevent the free flow of that um, quantity. So for electrical conductors, we allow the free flow of electricity. An electrical insulator prevented the free flow of electricity. And likewise for heat, a thermal conductor is something that allows for the free flow of heat, and a thermal insulator is one that does not allow the free flow of heat. So same thing, just different quantities are being involved. So reading again, as a result, air-filled pockets make extremely good heat insulators. Example, for home insulation, we have foam, fiberglass, double glazed windows. We don't really have that in Trinidad because we don't require to keep our houses warm as temperate climates where it gets to below 0 degrees Celsius in the day or the nighttime. And we want inside to be a nice 25 degrees Celsius, right, to be comfortable in. Example, same thing for bird feathers. These how birds are able to survive in cold climates. We have penguins in Antarctica, minus 50 degrees Celsius. They're not freezing to that because they have feathers. Feathers, what feathers do? There's a lot of space, there's a lot of air between feathers, and those feathers end up holding in heat. Same thing for wool, right? Wool holds in heat because wool is a very, very dense fiber, and you see all these little air spaces in between every single fiber holds air, holds heat. If you want to see a good way of how air holds in heat, all right, my two people who are here right now, try it look like this, or you all try without the fan on. Take your hands. Let me just stop the share for a sec. All right, stop the share for a sec. Take your hand cup it like this, right? Where it's not even, you're not doing this holding your hands together. Cup it like this, right? And within, say, like 30 seconds, you're going to feel the air heating up between your hands. Let me see if I start feeling. Right now, I'm feeling the heat already building between my hands. This is what an air pocket does. An air pocket holds heat. It's to the point where you can get it so hot you can take it and push it on somebody like that, and they will feel the heat move onto their face. Try it and see, right? My fan is blowing, so I won't feel it right now, but try it and see. All right, just build a little air pocket in between your hands here, and it's going to heat up enough where you can actually feel the air getting hot. Why? Because air holds heat. It's not a good conductor of heat. It's an insulator. Insulator means it holds the heat in. It doesn't allow that heat to move and transfer very far. So whatever heat is coming out of my hands is going to stay in that air pocket. So if you've never done it before, try it and see, right? Especially when the place a little warm or your hands are really nice and warm, you can actually feel the heat build between your hands. Let's go back to the share screen. We have a next example here. Water, right? Water is a poor conductor of heat. There's a simple experiment. Sorry, we're not in school to show this, but if I get any of you off a Cape, we have gas in school. We can probably do this if we ever let, allowed back on the compound. There is a little experiment. Is if you can take a Bunsen pen. Why are you not drawing? Oh, that's why I took off my glove. Right? If I have a test tube with water, so here they have a test tube with water, and they use a little piece of metal and you put ice at the bottom here. We can hold the end of one side of that test tube, and that water can start to boil, and you can have steam rapidly coming out of it, and you actually have boiling water, and we still have ice on the next side. Why? Because water doesn't necessarily conduct heat as well, right, as metals. Water is a poor conductor of heat, meaning it takes a long time to heat up, right? It takes a long time to conduct heat throughout, meaning the molecules here are hot, but they're not going to transfer their heat very readily to their neighbors. It's going to take quite a while, as in this ice will probably melt from normal processes as opposed to the boiling water. So it's going to take a while to melt. So this is a good little example. All right, this is our textbook example of demonstrating how water is a poor conductor of heat. We can cause one side of water to boil while we still have ice in the tube. And you can say, Miss, that makes no sense. How you can have ice and boiling water in the same pot, in the same container, but here we can demonstrate it and see. Look up some YouTube videos, you'll see it and find it, but I'm not a fan of YouTube videos. I rather see it in person. All right? That's the beauty of physics. We have to see it in person because we fed up see videos. I fed up see videos. Moving on to convection. Convection is the transfer of heat during the motion of currents. All right? Not electricity currents. Currents is something a little different. So let's continue reading. Generally, hot fluids, now a fluid in physics is classified as a liquid or a gas. So hot fluids rise and cold fluids sink. We've heard this forever. Hot air rises, cold air sinks for a reason. This sets up a current that constantly moves the fluid through a process of heating and cooling. Now, go and pay attention to water when it is boiling. Right? We're not talking about water, we're talking about rapid boil water. I think I already did explain this, so I told you all to look at it. When water is boiling, when we have a pot of water, folks, right? And we have, water inside that pot, and I have a flame. Right? So we have a flame under that pot of water. The initial part of boiling would be we'll have bubbles all through, and then we're going to see big bubbles rise to the top of the water. That's our stage of boiling. And then we're going to start seeing rapid boil. It's actually going to go through the circular process. Right? I told you all to look at this last time. There's a reason why it goes through the circular process. All right, this is called a convection current because let's see what's happening here. At the bottom, no, that's not bright marker. All right, at the bottom here, the water is going to be the hottest, obviously, because it's right above the flame. What's going to happen? Because hot materials rise. Why do hot materials rise? Why do hot gases rise? Why do hot liquids rise? It again comes to density. It's simply a dense situation. It has to do, when I have a set of gas, let's think about gas or liquids or any kind of molecules. When I have my molecules together, right? And I am now heating up those molecules. When those molecules move apart, and by moving apart, the volume of my liquid or my gas is now going to get larger. And because the volume is getting larger, the density is going to decrease. And because it's getting less dense, it's going to float. That's why balloons float, because their density is less than the things around them. Sorry. All right, that's all. Just like how ice floats because the volume is larger, reducing its density. Same thing for hot water and hot air, right? As we warm it, we cause the molecules to move apart, we cause the volume to increase, and when the volume increases, our density drops. And lower density is going to enable our system to float. Float means to move up higher. All right, so all our physics ties together now. We all tie together in one story. So as my molecule floats up, guess what? It's going to reach the air. Now the air at the top here is cooler than the air at the flame. Obviously, the air right over here is going to be cooler than the air at the flame. So because it's cooler, we are now going to give off some of that excess heat. And because it's giving off some of that excess heat, the water at the top is going to be colder than the water at the bottom. So here, my air is now cooling down. Not my air, my water is now cooling down. It's not cooling down to 10 degrees Celsius. You know, it's not a rapid drop, but it's still a drop. Right? If you put your hand right above a flame, don't put your hand right above a flame, that's stupidity. But we play with candles, right? If you put your hand close to a flame, you're going to feel the heat. If you put it further away from the flame, you're going to feel less heat. Same thing is happening here. So it's the point where it can lose a little bit of heat to the atmosphere and it cools down a little bit, and then it's going to drop. And when it drops, this is how we end up getting that circular motion. So it drops back to the bottom, reaches the flame, heats up, goes back up to the top, and then comes back down. So that's how we end up getting water going through this rapid circular boil, or we call it a boiling, a convection current. So pay attention to your water. If you're going to sit down and watch water boil, don't tell your mom that you're going crazy. Say, Miss Mom, I'm doing some physics, observational physics. Continue reading. Convection current and sea currents are responsible for our planet's weather. If we don't, if our planet gets too hot, our weather changes. If it gets too cold, our weather changes, and vice versa, right? When our weather changes, we are going to get hotter and colder days, which is what we're going through right now. You know, anybody who's saying climate change is not real, I think they lost part of their brain in a bowel movement. Serious talk. All right, so geography students, you should, right? Geography students, you all should know about land and sea breezes. Right, we have two types of breezes that occur, especially on coastlines, particularly on coastlines over by very large lakes and very large lakes. We have two types of breezes that exist. A land breeze is where breeze comes from the land and goes out to the sea, and a sea breeze is where breeze comes from the sea and goes into the land. Beautiful. We live in Trinidad. We have wonderful, beautiful Manzanilla and Mayaro, right, where we can see these things in action because we know Manzanilla is always breezy. I prefer Manzanilla to Mayaro, so I always speak about Manzan. right? Same thing for here. You all notice we are usually very breezy during the day and around say 6, 7 o'clock, unless we have a weather system in, the breeze dies. Particularly Grandview, here we're still close enough to the coastline to experience land and sea breezes to the point most time during the day, even early morning, it's a little breezy, right? And then during into the evening when we've lost the sunlight and whatnot, the air dies down. It gets completely still. That's because our breezes have now gone through a change, and we're going to look at why that change happens with the occurrence of land and sea breezes. So let's follow up. Right? One thing to remember, our sea, where did my marker go? Oh, right? Sea is water, made up of water, right? And water takes longer to heat up and longer to cool down. Land is basically earth, concrete, buildings, road, pitch, all these things. So land, because it's solid, takes far less energy to heat up and it takes far less time to cool down. All right, so always remember during the daytime, the land is hotter than the sea. Please note, we're talking about tropics right now. Let's not go and confuse ourselves with, where it's frozen and Antarctica and what and Arctic. All right, think about Trinidad here, using Manson as our example. So during the daytime, right, the sun here indicates daytime. Okay, yes, somebody has rolled their eyes and said, yes, miss, we know that. During the day, right, heat is delivered to everywhere, the surface of the planet, and our earth, our ground, our solid part of the planet is going to heat up faster than the water. So that means the ground here, let's get back to the red marker, all right? This is going to be hot, and the sea is still going to be relatively cool. So what's going to happen? Let's look at how the movement of air currents work. Just like how we did in boiling water, what's going to happen to the air above the land? Because the land here has hot surfaces, the air is going to rise, right? So all my air will tend to rise. Anybody ever notice that when it's really hot, it's hard to breathe? As in really, really hot, with no breeze around. If you all ever notice that, pay attention. Our September days are coming, right? It's not because you're imagining it or your mind's playing trick on you. When it is very hot, it is literally harder to breathe. Why? Because more air is moving up into the atmosphere. So the air that we are breathing right now will be a little less than it is normally. So it's not in your brain, it's not in your mind, it's not hallucinations, it's not anxiety. When it is too hot, it literally is harder to breathe. Right? Some people get used to it, like those who work by furnaces and whatnot, they get used to it. But for us in normal situations, normal climates and whatnot, when it gets too hot, it really does get harder to breathe. You are not imagining things. So that air starts to rise. And when it gets up into the upper atmosphere, that air is going to cool down. Right? And it's going to cool down and travel to a certain distance because there's an upper wind, because we have wind and breezes at different levels in our atmosphere. So that wind is going to get carried somewhere. Now, because it's in the upper atmosphere where it's cool, right, that's to tell you every 100 meters, the temperature decreases by 8 degrees Celsius. So it gets cool the further you go up into the atmosphere. Right, every 100 meters, like right there to right there, it can get cooler. Right, if you all go up on top of a mountain, any mountains in Trinidad, you're going to realize it feels cooler because we are further away from the ground. The further up you go in the atmosphere, the cooler it gets. All right, so when it goes up high, it's going to cool, and then because it's cool, it's going to reach a point where the air is now going to fall back down because it is now cold air. Now you want to ask, but okay, so I have cold air above the sea, right? That makes sense because the sea is not hot. The sea is nice and cool. So how do we end up getting breeze? Where does this breeze come from? So how does breeze end up blowing into the land? We understand that hot air rises, We understand that the air drops and is cooler down over the sea. What happens here? Because the air is rising, we end up kind of forming a little vacuum effect, right? With less air, same thing like how concentration, you all are chemistry students, right? We always have molecules want to move from an area of high concentration to low concentration. Guess where we have high concentration of air or higher concentration? Where the air is cold. Where are we going to have a lower concentration of air? Where our air is hot and rising, as in little bit, but enough to make a difference. Kind of forming a vacuum effect. So that means it's going to pull the air from the sea towards the land, right? Or the cold air is going to blow into the hot area because it's now taking up that space. It's sucking up that cold air from the land, from the sea. So this is how we end up getting sea breezes during the daytime, mostly during the daytime. We're going to discuss how it changes a little bit. Right, so we end up getting sea breezes during the daytime because hot air is rising over the land, creating a vacuum space for the cold air that has now dropped and traveled over the sea. This is why our breeze will be colder. You all ever notice when we have days where it's raining, it's been raining for a few days, right? And our breeze gets cool. It's not because there's not enough heat coming from the sun. There is enough heat to come from the sun to warm up the atmosphere, right? But because there is no heat, there's not enough heat to warm up the sea, right? The water that is the air that's blowing over this cold sea is still cold. Pay attention. If you've had no bright sunlight or something for a couple days, the breeze gets colder and colder because the air that's coming from the sea is colder, right? Or everything plays nicely into each other. So this is what we call sea breezes. Sea breezes come from a result of heat in the land, right? Air rising, cooling, and then we want to have cooler air dropping and then blowing into the land. And this usually happens during the daytime. Next one, land breezes. Land breezes is the opposite because in the nighttime, since our land cools down faster, our land is now going to be classified as cold, and our sea, because our sea has been warmed up during the day, it takes a longer time for that sea to cool down. So technically, land is now going to be colder than the sea. So we are going to have the warm air above the sea and the cold air above the land. So guess what? Since our sea is warmer, because it's now naturally giving off its heat, so this is not as intense as daytime. That's why night um, land breezes are never as strong as daytime breezes, because the amount of heat given off by the sea is never going to be the amount of heat going to be equal to the amount of heat given off by the land during daytime heating, where we have the sun heating up everything. So we're going to have the hot air rising, right? That hot air is going to travel along the upper atmosphere, right? It's going to cool and drop. Let's get a blue marker, right? It's going to cool and drop. And then because here had a little vacuum effect, high concentration to low concentration, we're going to have a breeze blowing out to the sea. So this is what we call a land breeze. Now, land breezes usually only happen during the nighttime. Why? Because the land has cooled down. Now, this has to happen to the point, it must be a special point where the land is now cooler than the water, the air above the sea, right? If there is no big difference in temperatures, there isn't going to be no land or sea breeze. So, for you all, I know beaches are closed and you probably never paid attention before, but next time you go Manzanilla, Manzanilla is the best place. Notice around, or you in a beach house by the beach. This is the best time to notice it. Around, say around 8, 9, 10 o'clock, or even 11 o'clock, you're going to realize that the air stops blowing, right? It's going to pause for a little bit, and then the breezes are going to reverse direction. It does reverse direction. It's not as strong and powerful as day breeze, but you do notice it, all right? I think it happens on the West Coast around 1 o'clock or 2 o'clock. Yes, I will know these times. I'm an astronomer. I'm outside whole day with a telescope, whole night with a telescope. So when you're waiting for clouds to move, you pay attention to the air. You know when to walk with your sweater. All right, so that's what happens during the nighttime. It takes a longer time for land breezes to set up because the air has to cool down above the land first, right? And sometimes it takes a while, depending on how hot it had gotten, for that land to cool down. It depends on how much cloud cover we have. You ever notice in the nighttime, it's warm in the night when we have cloud cover versus when we have no cloud cover because that cloud holds the heat in. When we have a lot of dust, Sahara dust, it's warmer during the nighttime because that dust is holding in our heat. All right, so that's why if you notice now, when we have a high Sahara days, like, yeah, today is a high Sahara day. I just looked at the mountains. You're gonna notice it wasn't so cool last night, and it probably might not be so cool tonight either. All right, so those are land and sea breezes. So pay attention to how land and sea breezes work. All right, so next time you all go to a beach house, I think we all need to go to a beach house once beaches are open. Just enjoy the quiet and the breeze. Not necessarily to go and bathe in the beach. Yeah, I miss a thing. Pay attention to how breezes work. Many people don't notice it, right? But pay attention to what time breezes changes because nobody at a beach house goes to bed at 9 o'clock. Nobody, right? So pay attention. You won't rest. You'll probably notice when the breeze dies down, like here in Grandy or surrounding areas, at a certain time of night, the breeze does completely die down. That's because our sea breezes have died out. Not to say they've gone anywhere, they've died out because temperatures are now equal. When the temperatures are equal, we have no more up and down movement of air currents. We've eliminated the vacuum effect, so we have no breeze happening whatsoever. Right? And that's actually why we have days where we have still air because there's no actual up and down movement, as in some areas are not cool enough or warm enough to have that up and down movement of your air. By the coastline, you will always have sea breeze because we are close to a water source, and that water source is always going to be some degree different to the land. That's the water experiment I've asked you all to check. And last one is thermal radiation, not nuclear radiation. Nuclear radiation is different. Radioactive radiation is different. All right, so let's look and see what we have. Radiation, thermal radiation. We have many different types of radiation. Heat can travel without the presence of a medium being air, water, some sort of gas, right? So it can travel through the emptiness of space. That is how we get heat from the sun. It has to travel through the emptiness of space, the 150 million kilometers. No, that's the moon. Sorry. Okay. I had to tell you the distance again. All right, heat from the sun travels through the emptiness of space. Heat can travel without the presence of a medium. It does so via electromagnetic waves, similar to light. They have a much longer wavelength than visible light and are called infrared waves. All right, remember we had done our full electromagnetic spectrum, and our electromagnetic spectrum is the range of energies that are emitted by atoms. Atoms, when atoms want to get rid of excess energy, they can do so by emitting an electromagnetic wave. And owing to the amount of energy of those waves, we have different classification of those waves. So just to run through, if you want, we have the lowest one is radio waves. Radio waves are emitted from atoms. And then we have coming up the scale. So along radio waves, we have long wave radio wave, we have short wave radio waves, we have microwaves. All of those are classified. Not the microwave machine earlier. Seriously. All right. Radio waves take up a really long, big classification because there are many types of radio waves owing to how big the waves are. Then we go to infrared waves. Infrared are waves that are emitted that carry heat. Then we have visible Roy G Biv, or visible light, Roy G Biv being red, orange, yellow, green, blue, indigo, violet. Then we have ultraviolet. Ultraviolet light is right after invisible light. Then we have X-rays, and then gamma. All right. Why I like to write down Roy G Biv, because guess what? In front of Roy G Biv, or the start of Roy G Biv is R, so right before it is infrared. Right? It's on the red side of visible light, and the same thing here. The ending, the highest part of visible light is violet, and right after that we have ultraviolet. So if you ever get confused which goes where, just think about Roy G. Biv being visible light. So before visible light is infrared, and after visible light is ultraviolet. Got little short little tips to remember your your sequence, because this does come from multiple choice, to put down the right um, order and levels of your electromagnetic spectrum. So coming back to this topic. Sorry. This method of transferring heat via infrared waves is called thermal radiation. Radiation is how heat reaches the Earth from the sun. This is also the mechanism by which the greenhouse effect warms the Earth. What is the greenhouse effect? Without the greenhouse effect, planet Earth will be uninhabitable. Right? We will not have enough heat, even though we're close enough to the sun. Our atmosphere will still be too cold to support life on it. It is because of the greenhouse effect we are able to have life on our planet Earth. So, what is the greenhouse effect? Let's get a bright marker. So, oi, right? Some of the radiation, what it does, radiation comes out from the sun. Remember, radiation is not just nuclear radiation. It's not just radioactive radiation. Any radiation means, radiate means to move in straight lines away from an energy source. So the sun gives off a whole bunch of electromagnetic radiation. It gives off radio waves. It gives off everything up to ultraviolet. Our star is not big enough to give off X-rays and gamma rays. It's not. Right? So through space, our ultraviolet light comes, our visible light passes, and our infrared comes to our surface of the planet. These infrared waves easily penetrate through our atmosphere, and because of um, certain greenhouse gases, it allows for some of those waves to bounce back into the atmosphere. Lots of it goes back out into space, right? Depending on the wavelength of that light or the wavelength of that wave. But some of those waves, because of the type of gases in our atmosphere, and what are greenhouse gases? Water vapor, carbon dioxide, methane, sulfur dioxide. Yeah, right? Those cause those heat waves to bounce back into the atmosphere. So what they do, they bounce back and they bring back heat, or they keep heat in the atmosphere itself. So we need these greenhouse gases to keep our planet warm enough to live on. All right, and these greenhouse gases move throughout the planets. We have areas where have higher values than others, but these heat waves bounce back and forth throughout the atmosphere, keeping our atmosphere nice and warm and livable. Now, everybody will say, but greenhouse effect, everybody talking and screaming and bawling and screaming about it. We have two types of greenhouse effects. We have the natural greenhouse effect, which naturally makes our planet livable on. If it was not for this greenhouse effect, we will not be able to live on this planet. Life would never have a rose on this planet. Never. All right. So we have here greenhouse gases. We have carbon dioxide, right? Water, methane, right? Sulfur dioxide. So there's a certain value, a certain amount that keeps everything in check, keeps it nice and warm. What we're doing here, we have an increased or rise in greenhouse effect because of the industrial revolution or the industrial age. We are now burning and pumping far more carbon dioxide into the atmosphere. We are now producing something that's not naturally found in the atmosphere, nitrogen, nitrogen oxide. Water, we'll always have water, right? We have more methane. We have far more methane. Why do we have more methane? Because we now have herds of animals grazing, right? As in, they can determine if we have a planet with life on it just by recording the amount of methane in the atmosphere. If a planet has more methane in the atmosphere, that means there are animals who are giving off methane gas, or there are rotting plants giving off more methane gas. Right? So, y'all, they can tell there's life on this planet due to cows giving off gas. Right? Gassy cows. It's exactly as it sounds. Right? So, because we've given off more of these gases, we are increasing the rate at which these rays bounce out. With more of these greenhouse gases, guess what? If we had, oh, English language is such a thing. All right. So suppose only when before nice normal atmosphere, right? All of these waves bounced off the planet, went out into the space, went out into space, and only two of them bounced and stayed in the atmosphere. With more greenhouse gases, guess what? We're going to have more waves bouncing around in the atmosphere. So we're going to have less heat escaping to the emptiness of space and more heat remaining in our atmosphere. So that is why it is warmer now, because we have an increased greenhouse effect. We're going to reach a tipping point where it's going to be too warm. That's what happened in Venus. Even though Venus is quite a bit closer to the sun than us, right? The reason why Venus is that hot because they have an extreme greenhouse effect where there is so much heat trapped in the atmosphere. The atmosphere is so thick. There's so much of these other gases in the atmosphere. Now, this is a natural greenhouse effect. They just had a runaway greenhouse effect, right? And the surface of Venus is hot. We sent down a probe and the probe melted. After some minutes, it melted because it was too hot. And Venus is hot not because where it is to the sun, right? It's that hot because of a very, very big greenhouse effect. Just to tell you all, people like to go and say, but miss, and volcanoes just give off greenhouse effects, greenhouse gases, and a volcano will go and spew out sulfur dioxide and all this stuff. The amount of greenhouse gases that a volcano emits, right, when it's erupting is how much gas we emit one day. All the volcanoes on the planet could go and erupt, and we can take all the gases of them. That's how much greenhouse gases we pump out in one day from industries. So volcanoes don't really add to anything. They've always been there. It's because of volcanoes, their contribution, the gas that a volcano emits is what contributed to the atmosphere being livable. All right, so people like to complain about volcanoes. If it wasn't for volcanoes, we wouldn't be here. The planet wouldn't be livable. We'd have no land and it would be too cold. All right, and last one is how greenhouse houses work. In temperate climates, they realize, we can make an artificial greenhouse. An artificial greenhouse, what it does, there's a certain type of glass. What it does, use glass, and what happens, the heat that comes through the glass, because infrared waves will travel through a transparent material, only some of those will end up coming out of the glass. Right? They can come through it, and if you have the glass of a certain type, the infrared waves will not all come out. So what we end up doing, we end up getting gas or waves bouncing around in the greenhouse that is heating up the air, making it nice and warm, and able, for you to all to plant crops and stuff. And as in, people plant enough crops to maintain a whole country in their greenhouses. Right? You can't afford to have your crops die for half the year, because some places winter and autumn and spring is half the year, more than half the year, where the land is not plantable. You cannot get crop, you cannot get goods from. All right, let's just think about it. You don't want You can't just get lettuce for 5 months a year. You want lettuce for the entire year. You don't want tomatoes for 5 months of the year. You want tomato for the entire length of the year. So this is what we have greenhouses for, right? A greenhouse is one that keeps in the heat from the atmosphere, from the sun, right? And it prevents the heat from being lost to the atmosphere or getting too cold. We will have a little session on how to do calculations for greenhouses because that is part of your syllabus. So we will go through that on next day. But that's going to wrap us up, yeah, for methods of heat transfer. And if you want, we can go through the last version, how heat transfer works in our atmosphere. We get heat traveling through space, traveling through air by radiation, right? Thermal radiation is where heat travels through air or space. If you all go out, a good way of determining or checking some thermal radiation, go out in the sun, like right now, hot sun, for like 5 minutes. Come back inside and then put your hand right close to your head. Don't you feel heat radiating or coming off from your head? You can actually feel the heat some distance away. That's not due to conduction because you're not touching your head. That's not due to convection because convection must be a circular motion of heat and cold, right? So what's happening? You are actually radiating heat. That heat that radiates off your head, as in if you put your hand close to your head too without a breeze flowing, a fan on, but try it again. Put your hand close to your head, not touching your head, and after a little while you will be able to feel the heat radiating off your head, and that is because you are also giving off infrared waves. Those thermal guns that everybody uses now, it doesn't have no laser. Whoever is saying that, chip it, right? What it does, it is able to record the amount of infrared waves coming through the air, and the infrared waves um, enable something called the photoelectric effect. The photoelectric effect is when we use waves of a certain wavelength, it causes electrons to be liberated from certain metals, and we're able to record that current. And by recording the current, we could record the temperature. So that's how we use those thermal guns on somebody. No, we're not firing anything into anyone. If you see a red light, the red light is just to make sure that you focus the gun or you focus the receiving part in the right spot. It's just a red light. They could have used orange or green or purple or blue, but they end up using red because red indicates infrared waves, and infrared is the red side of the heat scale. We've color coded everything. There's a reason why it's a red light. Red light indicates that we're checking infrared waves. Color coding. So what it does, you put it close to that's why it has to be a certain distance away, close to your head, and the infrared waves that you are naturally emitting, as long as you are alive, you are emitting infrared waves. The infrared waves pass in through a little test window, and that test window records the temperature by using a different electrical value. That's all it does. All right. So people who are telling you these things giving you radiation, it's about no, I am the one giving radiation, not the gun. All right. So y'all don't be afraid of them. And ideally, you're supposed to be using your head or your neck to record those temperatures because we went through this last day. When you're sick, your mom does this, puts your hand on your head to record to check to see if you're hot or not. Nobody does this, comes and hold your hand. I think you have a fever, by holding your hand. You'll watch them like they're crazy. So why are we testing here for our heat? This is our arm. Our arm is not the same temperature as our core body. Right? So we're supposed to be using those guns right here, right? Either on your forehead or by your neck or by your core body. But y'all, I have given up on trying to teach people physics who don't want to learn any physics. So that's why we are able to record heat, because we give off infrared waves too. Right? So we have heat reaching the ground by infrared radiation. The ground conducts heat because it's a solid, and solid conducts heat. And then what we do, we cause the air above the ground to rise, to cool, to warm up, and that rising and cooling air forms our convection current or circular current. So that's how we have convection. So our atmosphere and our planet has all three forms of heat transfer to move our heat around. And without a proper movement of heat, our climate breaks down, our weather isn't affected, which is what is happening now. But that's the next story for next time. All right, so y'all, that's going to be it for this session. Next day, we're going to move on to heat energy and we're going to wrap up the syllabus. So, bye bye. Let me stop the record.